Alright, next to enhancement STP. So the problem with STP is it takes a minute, and 1 minute is too much. First of all, in 1 minute, all the TCP links will break because it may time out. TCP connections have a timeout and they will not hear the traffic for some time and they will break, and which is not good. So they have invented something called rapid spanning tree. And we will go through that in a minute. And then the second problem with this is that this works, if it doesn't work with VLANs. VLANs we haven't talked about, so when we talk about that VLAN, we'll talk about as to what it does is. So we need many trees for VLAN, so there is something called MST, multiple spanning tree, which was invented, which was done basically in 2002, 2001. And so we will see all that, right? So rapid spanning tree. So the goal of rapid spanning tree, which was again, you see, notice this little w. Little w means what? It is just an enhancement which will disappear and merge into the main standard. So this was an extension to 802.1d and merge into 2004. So D will have many versions, and if you go back and see the history, you might find like 99, 97, 2000, 2001, 4, maybe 11. So every few years they just take all the enhancements and put into the main standard. So this is an extension and this is the main standard. So today if you want to go and find it, you really want to go to 1D. Normal spanning tree takes a few minutes, which is not good. So RSTP fixes it by two different tricks. First trick is that it makes it not one periodic but also event driven. So the thing is, STP is basically it is periodic as well as event driven. So periodic means every few seconds we want to make sure that you are alive, right? And event driven is that when I don't hear from you, I know that you're dead. And so here we do both. If something dies, and you know how we know you're dead is because even if you're not talking to me, the zeros are sent on every link all the time. All right? So if I don't hear any zeros from you, means you're dead. So either you are dead, you are not alive, or because and every 2 seconds I just check, even in spite of that traffic, I check that you are still not only sending zeros, but you are still, your brain is working too. Because you might be stuck at 0. So those two things are done: time driven and event driven. And so what happens is, once the STP is converged, in the STP, in the original spanning tree, once you converge, then the BPDU is bridged PDU, bridge PDUs. PDU is protocol data unit, okay, and bridge is the protocols. Bridge protocol data unit. This is an OSI term, PDU, right? So BPDUs are sent only when there is a change. Otherwise, you don't bother to tell the neighbors that my address is 1 and the route is 101, and then you can reach the route with cost of 2. You don't tell anybody that. You just did it in the beginning, and then you are done. And here, you send an hello every 2 seconds. And so that way, if something fails within 2 seconds, you will know. By the way, 2 seconds is the default. You can make it 1 second if you want. You can make it anything less than. The more smaller you make, the more control traffic you have and overhead you have. See, the thing is, there is, as I said, you can make it half a second. And if you make it half a second, you'll have 4 times more hellos and less data traffic. So it's just what we call the expert's intuition, is that there are a lot of expert people who are designing switches and everything and monitoring the traffic. They are in the standards room, and they say, okay, the default is 2 seconds. Particularly when it was 60 seconds to find out. Now they can do in 2 seconds. That sounds like an order of magnitude improvement, right? And maybe today they might even not like 2 seconds, but that is 10 years later. All right. Differentiating between the edge ports and the server. Second thing it does is it differentiates between the hosts and the switches. Now they know that the hosts have no path out anywhere except to the switch, so the host don't see the hosts have to know the spanning tree because they have to know where to send it if they have whatever it is, right? So the host who is the designated bridge, for example. But here we differentiate between the edge ports and the switches, and we know that the loops are not going to be found on the edge ports, so they don't contribute to the loops. The only loops are contributed by the bridges. And we differentiate between point-to-point links and the half duplex link. Full duplex is the point-to-point, and half duplex is that shared link. CSMA CD is half duplex. All right. So we distinguish. And RSTP is used only on full duplex, which is 100% of the links these days. As I said before, CSMA CD is not used anymore. So this picture is only for teaching you guys 473, but not a real world. In the real world, the picture is more like this. Okay? Everything is point to point. All right. So a rapid spanning tree will not apply if you have the old CSMA CD stuff. Obviously, if you are a bank or a Amazon or Google, you will not have it. There might be some old building left where they might still have it, but the switches are so cheap that if you haven't replaced them in 10 years, I don't know what you're doing. So so they have all been replaced. All right, so let's see how it works. Oh, the fourth continues. The list continues. Fourth thing it does is it merges. There were lots of states which we actually did not go into one called discarding. So previously, a port could be in disabled state, in blocking state, in listening state, and so on and so forth. And it doesn't really matter right now because we have a lot of other things to cover, so it doesn't matter. Adding 4 new flags in the BPDU. So there are new flags which allow sending a proposal and accepting or not accepting the received proposal. So now there's a negotiation. So you might say to look, I think we should disconnect this link. You say, no, I don't want to disconnect it. And so that is called a proposal. And so there are some bits which say, here's my proposal, and you say, well, I accept the proposal. And it is fully backward compatible with STP. If you have any STP, then RSTP is not used. So that is how it is fully compatible, is that anybody who speaks RSTP also speaks STP. But if they find a neighbor who does not speak RSTP, they say, okay, all right, you don't speak RSTP? Okay, we won't use it anymore. We'll just use STP. Okay? So let's see an example here. So here is a network. Here's the network. You see the root is connected like this. This is, you even can say this is a tree or this is a line, whatever, but there's a network. Fully connected. And suddenly this link is connected by somebody, R to A. Initially it will be blocked because, we never saw this before, but in 2 seconds we will know that there is a path. Right? Now, in the original spanning tree, we will say to the whole world, oh, new link has come up, let's just, do all the whole thing, and it will take 1 minute. In the new case, this will say, oh, I am the root, and which they already knew that this is the root, because A knew who is the root, and A knew that 3 hops away. But now it knows I have only 1 hop away from the root. So it says, oh, let's bring this up rather than the other links that I have, and I will block the other links. So it takes that link as accepted and blocks these 2 links. It basically sends the proposal to B and C and says that I am going to block these 2 links because I have a shorter path to the root. Then B and C think about it. Now B is the edge node, has nothing to say, okay, all right, whatever you say, boss, I'm fine. And, actually no, basically the B says that, okay, all right, you are my only connection, I'm already going through, previously B was going through A and it will continue to go through A, so that will come up. And C will find that this is a shorter path, is it? CDA, this is 2 hops away, and this is now 2 hops away. So it's up to C to decide whether to take this shorter path or not. Right? So it is quite possible, I think as drawn here, my feeling is that C might take this, C might stay where it is, and then this link will be blocked. Okay? This link will be blocked, this link will clear, and this link, C will use this link which is also 2 hop away. Now the only difference is that if this link which is shown by the long distance has some reason to be longer than this path, then it will say, okay, I have a shorter path. So basically, C accepts and blocks CD. As shown here, C accepts the proposal and blocks CD, so then it has a two-hop path through this path. Okay, now the whole network is basically, let's say, converged with two proposals, one going here and then one going here to maybe 4 to 6 seconds. Okay, RSTP. So this is rapid spanning tree. Now, multiple spanning tree is the next one, which came in 2002. You see, this is D and this is Q, and that is correct. Rapid spanning tree was incorporated into D document, which is mostly for the bridging, and this is incorporated into Q document, which is mostly for VLANs. So the multiple spanning tree is required only if you have virtual LANs, and since I have not explained virtual LANs, you just basically I have to just give you a brief. This thing is that you can have many different types of traffic in the same network. So here we have three kinds of traffic: black, red, and green, red and blue. And everybody who is blue is here. This is very simple condition, so on. So basically, this is red switch, red network. There's a black network and there's a blue network. But this part is shared by all kinds of traffic. So there will be a blue spanning tree, which route, this is the route, and it goes to these two. There will be a red spanning tree for which this is the route and goes like that, and there is a black spanning tree which is for this is the route. So there are three trees here. So each tree serves a group of VLANs. It is not necessary that you have for 3 VLANs you have 3 trees. You could have 3 VLANs and just 1 tree or 2 trees. Alright. So a group of VLANs are serviced by a tree. And which group is all administratively defined. So when the VLAN is defined, at that time the manager says, okay, you set up a blue, you are part of the blue VLAN, and this blue LAN will use that spanning tree and whatnot. So all that is done by administratively. But anyway, this allows you multiple spanning trees. And because of that, it could be in forwarding state for some VLANs and blocked for others. So for example, this one is blocked for red, but it is forwarding the blue and the black traffic. This is blocking what kind of color? What color? Black. Because the black tree is just like that, right? And so this is blocked for the black. So no black traffic can cross this link. And this is blocked for the blue. There are several, 2 reasons first of all. Not all VLANs go all places. Even though you have one network, red VLAN cannot come into this building. It is president's building, very secure and things like that. Okay, so not all VLANs go to all places. So that is one simple reason, that you don't want to basically use the same route and same everything. Each VLAN is basically complete in itself. They don't know actually. The VLANs guys don't know that they are sharing anything with anybody. So they have their own spanning tree. Although, as I said, they could be sharing a spanning tree too. Like, each spanning tree serves multiple VLANs. No, there is no IP so far, and in this whole lecture, I will not use the word IP. This is data center Ethernet. I haven't talked about VXLAN. This is VLAN. We'll talk about VXLAN when the time comes. That is actually 2 or 3 lectures away. So basically, right now we are at layer 2, and we are not talking anything about layer 3. The only relationship is that the LAN traffic does not go through a router, right? You know that. The LAN broadcasts do not go through a router. So the VLANs cannot be passing through a router. If the LANs stop on a router, the VLANs will stop on a router. So I'm going to come to that part when we come. So there is a lecture which is actually 2 or 3 lectures away where we talk about extensions to Ethernet for data center. I haven't talked about VLANs, but I think that is the next thing. It's coming up in a minute, VLANs. So the maximum VLANs allowed by the first standard, which is 2005. Well, 2005 may be the second one, I don't know, second revision. But by 2005 or so, they allowed only 4,098, 95 actually to be exact, 4,095 VLANs. And that is not enough in a data center. So they have new extensions which allow more. Now I'm going to talk about a protocol, IS to IS, which is not even a TCP/IP protocol. It's a OSI protocol, which you have not been taught, I guarantee, in 473. But it's very similar to OSPF, except that this is not a TCP/IP. TCP/IP uses OSPF. OSI uses, actually was hoping to use IS to IS. So it was designed very generally, and therefore it is used at many places. IS to IS is used very many places. It's like OSPF. The main difference is it is not dependent upon IP. It does not require IP addresses. You can use any address. You can use IPv6 address, v4 address, MAC address, any address in the address field to exchange. So that's the strength of it. It's a general purpose route table making protocol. OSPF is a routing protocol, right? It makes a routing table. IS to IS is more general than OSPF because it can make the same routing table, but for any other addressing that you're using. All right? And IS stands for intermediate system. And what is an intermediate system? That's what we call router in the TCP/IP world. In the OSI world, there are two kinds of systems. Intermediate and ES is the exterior system. Exterior and interior. ES. Okay. So basically there is a end systems and the interior systems, right? The edge systems or whatever. So basically intermediate systems is same thing as a router or anything. So here I think this is also a general term than router. Even the switches are intermediate systems, right? Switches are going to use this in a minute. IS to IS. So IS to IS is intermediate system to intermediate system protocol to build routing tables. It's a link state routing protocol. So now, this is where your 473 comes into practice. Does anybody know what is the opposite of link state? Or what is the alternative to link state? And like there are two kinds of routing protocol, link state and distance vector. So the idea is that there are two kinds of ways of finding your route or finding the whole graph of the network and finding the shortest path and all that, is that you tell the whole world about your connectivity. So I tell that I have two connections, but I tell everybody, I send 19 messages, one to him, one to him, one to him, one to him. To the whole world I say that I have two connections. Or I tell to my neighbors only, but I tell the distance to everybody. So I say, well, I have one hop from him, two hop from him, three hop from him, four hop from him. So that's the distance vector. It says long vector because there could be 2,000 of you. But I tell you only two people. Right? So distance vector, and those are the two methods of telling the whole world where I am. Right? And then the whole world can then calculate. So link state is better actually, and that is used by OSPF. Before OSPF was a protocol which I forget the name. What was it? Routing protocol, RP something. Anyway, so that was distance vector, and that had its problem. Anyway, so OSPF is link state, and link state is what we use everywhere. IS to IS also uses link state. So that means end nodes send its connectivity. Actually, I should not end node. Each node sends its connectivity. That means the link state to all the nodes in the network. Okay. Then they use Dijkstra's algorithm. Everybody knows what is Dijkstra's algorithm, right? That one they teach, right, in every place, I hope. If not, then you have to look it up, because then I would be going back to 473, if nothing else. So Dijkstra to find the routing table. It is similar to OSPF. OSPF is designed for IPv4 and then extended for IPv6. IS to IS is designed. It can be used with IPv6 without any extension. It can be used with IPv4 without any extension. We are going to use it here for Ethernet without any extension. OSPF is designed to run on the top of IP. IS general, it can run on anything. So it can be, that's why it was adopted by the IEEE people. So now what we use is what we call shortest path bridging. 2012. Obviously, this is not in the books, but it is in practice, it is being used. So, shortest path bridging is basically all the switches exchange the link vector and find out what is the shortest path to go from server 1 to server 4, or from anywhere to anywhere, right? So they will figure it out. If I want to go to server 2, all I have to do is go to switch like that. If I want to go to something, I have to go this way and that way. And not, so basically that is the shortest path. So now all the links are used. You don't block any links. And that way it is called better CapEx. What is CapEx? So the people who manage these data centers, they have two kinds of expenses: capital expenses and operational expenses. Operational expenses are things which you have to do day by day. Capital expenses are things that you buy and then you just gone. Right? Operational expenses are including the operator and electricity and things like that, right? And the CapEx is buying the equipment, power supply, generator, those are all CapEx. Running the generator, you need the oil, that is OpEx, right? So, OpEx and CapEx, so this is better CapEx. Because once you bought the link, 100 megabit, 1 gigabit, 100 gigabit, whatever, you want to use it, right? You don't want to block it. So, this is the one. IS to IS protocol is used to find the shortest path, and if there are multiple paths with the same distance, both of them are used with equal cost multipath. So, basically, you hash and you decide, randomize, and you decide as to how to get there. There are two paths here. From server 1 to server 4, you can go by the red path, or you can go by the blue path, and you will use both. Half of the packet. Not that you will send first packet here, second packet there, because that would really cause confusion. Because if the links are not the same distance or same congestion, some packets will arrive out of order. So you hash so that all the packets which have certain thing in the header will follow one path. Other packets which have something different things in the header will follow other path. All right, it might be the IP address, and so you just hash on little bit longer than into the packet. Equal cost multipath is used. So now you are using all the capacity. You bought two adapters. You bought for two links. You are going to use both the links. Red path and blue path, they have no common links. See, what happens is, what this switch knows is that I am 2 hop away from server 4 on red path, and I am 2 hop away from server 4 on the blue path. It will decide between the two of them and then send it here. Now this switch will then decide how many hop away I am from here to there. If there is a common link, then it doesn't have to make that decision. If it has two different paths, then it will decide that I want to send it here or there. So although I have shown you the red path here, this is not something that this switch controls. This switch only knows that I have two alternatives here to begin. It's just one hop decision. If there is only one link, yeah. Say, let's say this blue link is down. By the time it will figure it out that there is no, the path is not shortest path, because this IS to IS will figure it out. You know the complete. Basically, the idea of IS to IS is, OSPF or anything, is that you have the complete graph. Every node has a complete graph of the network. So they can figure it out, right? That there is only one link here and so on and so forth. And even if there is a common link, that's not bad, because if you have two paths, let's say you want to go from here to California, but you have two paths up to Kansas City, and from Kansas City you have only one path. It's still better that half people go through this path and half people go through this path to Kansas City. From there is no choice. Or let's say you have one path from here to Kansas City, but there are two paths from Kansas City to California. It's still better to take those two paths and use them, right? So it's okay. Is there a disadvantage to this protocol? Well, this is just a lot more work, I would say, at this point, first of all. Second is that it is new, so not all the switches may know. If some switches don't know, then you are in trouble. You will have to fall back to your old system, which everybody knows, right? If suppose you don't speak IS to IS, then I can't really make a whole graph. You won't tell me that my distance, to who am I, right? Things like that, right? So basically that is the thing. Is this is new, and everybody has to speak it. It's more complex. What else can I say? And the second thing is, it is only 2012, so we will know the problems in 2014 when we have something else, STP version 2. Right now, this is too early to say anything negative. See, the original Ethernet, when it was designed with the KISS principle. Everybody understands KISS principle? KISS? Keep it simple, stupid. Right? And STP was that. Spanning tree was that. It was not optimal. It was not optimal, we knew that. But it was simple, and so that was fine. Now people are saying, no, we cannot be so stupid that we put a 100 gigabit link and not use it. So we are just, getting rid of the last S. As much, because the first S becomes a little bit complex.